So this video is going over the Chapter 3 multiple choice review problems. Okay, so number 1 is talking about they give you a correlation value or an R value of 0.94, but they want to know why it does not necessarily indicate that linear model is the most appropriate. So they're really talking about all the parts of like Duff's direction, form, and strength, and what things talk about which things. Okay, so 0.94 is close to 1, positive 1, but keep in mind that R values, be it 1, negative 1, or 0, those are about strength, not form. And right now we're talking about form. We're talking about whether it's linear or nonlinear. You could have something that's actually a pretty close to 1 or negative 1, but also has a slight obvious curve to it. And in that case, linear isn't the best. So that's about strength, not form. This one is talking about, remember that causation does not necessarily equal correlation. Just because two things have a strong relationship between them does not mean that one is causing the other. D is talking about R squared. If you square root 0.94, which I'm pretty sure that's the case. Let me double check on my little calculator. Where did they even get that from? 0.94 squared. Oh, there we go. Okay, I did that backwards. My bad. Let's try that again. If you do 0.94 squared, so you're getting R squared, you would get 88%. But let's think about what that means. This wording is close, but it's not in the end right. So this means that 88% of the variation in your Y is explained by your least squares regression line. It doesn't necessarily mean that a line is the best way to fit it. So like 88% of it could be explained by a least squares regression line, but that it just doesn't really work that way. It's like saying it's mostly good with a line doesn't really tell you if it could be better with something that's not a line. So it's just not using the words correctly. Now, E is your answer. So even with a correlation value of 0.94, it's possible that it could still be better represented by a nonlinear model. So let me just give an example. What if it was something like this? So it has a pretty high R value. You could put a line through it and the points wouldn't be very far off of it. So it has a pretty high R value, has a pretty high strength, but clearly looking at your original data, there is a curve to it, and linear is not the best option. Something curvy would be better. Okay. Number 2, this is one where basically they're saying, does there appear to be evidence that more time spent playing makes the sooner the cub is ready to hunt? So high playtime is what they're asking about. Does that go with lower age when they first start hunting? That's what they're wondering about. So that is true for the females. If you look at like this point, it has a very high playtime, but a low age. And then on the flip over here, it has a low playtime, but a high age. So there's that reversed relationship there. On the males, it seems like it doesn't matter how much they play. They're ready to hunt all in about this range. That the playtime doesn't seem to have any effect on the hunting time. So I would say this is true for females, not for males. So there we go. A for female cubs only. Okay, for number 3, for which of the scatter plots is a correlation between X and Y closest to 0? Now, probably when you first read this question, you thought, okay, I'm looking for the one where it's all randomly scattered. I'm looking for a random scatter. And then you go through your answers. You kind of zoom down now, and you're like, uh-oh, none of them are randomly scattered. So there's something more complicated going on here. Okay, so let's narrow down the ones we know for sure right off the bat. This one is pretty much exactly a line. So this is really close to an R of -1 because it has a negative slope. C is really close to an R of +1 because it is a positive slope. So now we're down to kind of the curvy ones. There's B, There's D, which looks a lot like B. It's just going up rather than down. And then E is this other thing. So let's think about B and D. A line won't fit it perfectly, right? But I could put a line through and it would still represent a big piece of what's going on here. It's not representing the curviness, which on a side note means linear. This is nonlinear. There is like a cubic function or something that has bobbles in it, waves in it, that would be a better fit. So it's nonlinear, but it is going down over time. As x gets bigger, y gets smaller as an overall pattern. And a line would at least represent that. Same here. I could put a line through on D. It is nonlinear, but at least the line would show that it's going up over time. Now here, boy, the best line I could put through it is, I guess, right through the middle. And that's not representing anything useful. It is showing that like there's clearly a pattern to the points there, but that line is not representing any of that. You're not getting any useful information out of the line. So that's why this is your worst fit. So mathematically, it would have the lowest R, closest to 0. That line doesn't show hardly anything about that relationship. So it has a very low, weak correlation. Okay. For 4, okay, so we have this scatter plot and we have an outlier over here. It says if point A were removed, which of the following statements would be true? And looking ahead to our statements, we're looking at the slope and the correlation coefficient, or R. So those are the two things we're going to have to think about. Okay, so I'm going to put a line through here, guesstimate a line here. And you can imagine if this is our line, including with A there, A is acting like almost like a force is acting on it. Imagine A is like a magnet and that line is like a metal bar or something, and it's pulling that metal bar towards it. And remember that we learned these least squares regression lines it's like they're a seesaw or a teeter-totter. And they always teeter-totter around the point x bar, y bar. X coordinate being the average of all the x coordinates of all the points. The y coordinate being the average of all the y coordinates of the points. So it's like a seesaw, like a teeter-totter. And that outlier A is pulling it towards it. And so let me use a different color. If you took A out, so if I take A out and therefore that force is gone, it's going to snap kind of back up here, which makes it teeter-totter down there. So let's think about what happened. Our slope got steeper, and it's a positive slope, so it got to be a higher slope. And our correlation coefficient, our R, well, with taking an outlier always increases the correlation coefficient. Now that green line is a better fit to the points. A was an outlier, so it was always kind of a bad fit in bringing the correlation coefficient down. So slope went up, R went up. And so that's why C is your answer. Okay, so for 5, what do we have here? We have a least squares regression line. We have a domain. So they're acknowledging how far is too far and is therefore extrapolation. They're saying this pattern only really works for data between 9 and 25, and they're not saying anything about data beyond that. So anything lower than 9 or above 25 would be extrapolation and would be a bad thing to do. Okay, so what's an increase in temperature that corresponds to an increase of 5 trips per minute? Now, notice this word increase. I'm just guessing after years of grading people's tests that people will see the 5 and they will plug it in for X and get an answer and call it good. But they didn't say 5 chirps per minute. They said an increase of 5 chirps per minute. So watch for that. It's about careful reading of the question. So there's a couple ways you could do this. One is to think about what the slope is. Okay, so the slope is 3.3, right? So they're saying there are 3.3 and y is the temperature. So there's a 3.3 degree increase for every additional 1 of x, and x is chirps. So every time you add a chirp, your predicted slope would go up by 3.3 degrees. So we could make this proportional. If we're interested in an increase of 5 chirps, it's just 3.3 times 5, which gives you something. 3.3 times 5 on my calculator is 16.5. So that is one way to do it. Say the slope talks about what happens when you increase x by 1. So if we're increasing x by 5, it should just be 5 times the slope. That's one way. Another way is a little bit more of a brute force way. Let's just pick 2 points that are 5 away from each other as far as x's, plug those in, and see what we get for our increases. So if I pick, let's see, 9 is our beginning. So if I go 25, let me do a different color so it's clear when you read it. It's a different method. Okay, so 25.2 plus 3.3 times 9, you get something. 3.3 times 9 plus 25.2, I get 54.9. And then try another point that is 5 above that. We're looking for an increase of 5. So 5 above 9 would be 14. So 14 times 3.3 plus 25.2 is 71.4. And then if you go 71.4 minus 54.9, you get 16.5 as well. So I just picked 2 random points that were 5 apart. I picked 9 and 14. You could pick 20 and 25. You could pick 12 and 17. Any of those should still give you that value of 16.5. So 2 different ways you can do it. One more conceptual, one more just brute force by plugging things in. Number 6 is about reading the computer outputs. Now, these will show up on the test. They'll be in the multiple choice and in the free response. So make sure that you are able to read these. Make sure that that paper I had of pointing to what is where you have out. Either that paper or you have a Post-it note to pages 191, 192 in the book. And you can flip to it and look at it that way. So in fact, I'll write it over here too. Page 191 to 192 in the textbook. So make sure you look that up and have it ready to go for the test. So you can always go look up what things are. So quick review of what's in here. We are interested in the slope in this problem. So here's the slope. That's our B. This is our A. That 264 is our y-intercept. This is our explanatory variable, your x. We have S. We have r squared. So you could say that r squared, if I were to write that as a decimal, is 0.557. So you could also say r is the square root of 0.557, which I do on my calculator, and I get 0.746. And we don't know if it's positive or negative until you look at the context. And they didn't tell us. You could make a guess based on real life, but they didn't give us any more data. So the R is either plus or minus 0.746. Probably it is, I'm not really sure what lean body mass is. Is that just regular weight? I don't know. So it's positive or negative. If you needed to know that, it would be given to you. I'm only just going into more detail here because this is your chance to review. Okay. And then the other reminder that a bunch of this stuff, this is all stuff for later on in the course. That we never use. So just cross that out. That's not useful to you. Okay. So the slope, what's the best interpretation of the slope? Well, if we know our x, our explanatory variable is mass. And remember that slope is change in y over change in x. So if the y is not mass, it is resting metabolic rate. So that's y, change in resting metabolic rate over lean body mass. So we are finding out that for each additional kilogram in lean body mass, you get an extra 22.563 in resting metabolic rate. So 22.563 over 1. Okay, so for each increase in mass, we get 22.56 in metabolic rate. So let's find the one that matches that. So for each kilogram of lean body mass, resting metal increases, there we go, 8. 8, A, I mean. All right. Which of the following is the best description of a positive association between two variables? Well, positive association is, I don't know, something like this. A line with a positive slope. So notice that your high, like if you look at this point, your high x coordinates go with high y coordinates. And your little x coordinates go with little y coordinates. Okay, so value as one variable increases. So as x gets bigger, y also gets bigger. Okay. A, the values will create a line when graphed on a scatter plot. Positive association is just about direction. This one is about form. We don't know. Just because the overall least squares regression line would go up doesn't mean that it's not curvy and that there isn't a nonlinear thing out there that's better. The values will create a line with positive slope when graphed on a scatter plot. Again, yeah, positive slope, yes, but we don't know that it'll create a line. And all values of both variables are positive. It could be something like this. Maybe negatives make sense in the situation. So we don't know that all values are positive. We don't know that it's contained to that upper right quadrant. Okay. 8. 8 is one where they give you a whole lot more information than you need. They're saying, if a linear model is appropriate, what should be apparent in the residual plot? So that if a residual plot has no pattern to it, then that means linear is the best function family we're going to get. So there's no pattern in the residual plot. It doesn't tell us anything about direction. All points must have residuals of 0. It means it makes a perfect line. We don't know that. And this is getting you mixed up with, oh, that's a tricky one, because that goes back to the information they gave you that you didn't need. If you have thickness here and you have pollution here, they're saying thicker filters create less pollution. So they're saying they're getting it like this, and it's getting your brain primed around kind of like what we did in the last part, the last problem, but that wasn't what they asked. They asked about residual plot, and what does that tell you? So I'm just going to say here, not what was asked about, but they primed you to think about it because it's extra information in the question. It's very tricky. Look at that. We're done. All right. That's it.